In this video I am going to explain you about some of the questions from atomic and molecular physics. So before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. So here is the first question. Match the following. So the first one, Frank-Hertz experiment. Here they have given these different experiments and whom they have invented and what is the role of these experiments. So the first one, Frank-Hertz experiment, was performed to identify energy levels in atoms. So this is option fourth one, and Hartree-Fock method that is used for the wave function of atoms. So second option itself. Then Stern-Garlach experiment, obviously it is was performed to check the space quantization of spin angular momentum of atoms. So option 3, Frank-Condon principle. So here the left option is first one, electronic excitation of molecules. So the Frank-Condon principle gives the electronic excitation of molecules. So here if we see these experiments, what they are going to explain, option A is going to be correct here. P4 option A, here option A is correct. So P4 Q2 R3 S1. So next question is light of wavelength 1.5 micrometer incident on a material with characteristic Raman frequency 2 into 10 to the power 2 Hertz results in a Stokes shifted line of wavelength. So here we need to find out the shift in a wavelength. They have given here the light of wavelength having 1.5 micrometer, which is going to incident on a material with Raman frequency 2 into 10 to the power 2 Hertz. So we have the equation that is going to relate with frequency and wavelength, that is nu is equal to c by lambda. They have given the value of speed of light. So if we substitute value of speed of light and wavelength, we will get here the frequency that is given for the wavelength 2 into 10 to the power 14 Hertz. So the frequency of wavelength of light 1.5 micrometer, having the frequency that is 2 into 10 to the power 14 Hertz. This will be the exciting line, that is Rayleigh line, and the frequency of Raman line is as they have mentioned here, that is about 20 into 10 to the power 17 Hertz. Therefore the Raman shift we can calculate from these two frequencies, that is going to be 180 into 10 to the power 12 Hertz. So 10 to the power 14, if we make the power same, then we will get 200 minus 20, that is 180 into 10 to the power 12 Hertz. This is 10 to the power 12 Hertz. This should be 20 actually in this question. Then in terms of wavelength, the Raman shift is given by, this is what frequency, shift in the frequency. Then the wavelength shift we should calculate, that is 3 that we can calculate by taking the ratio of what according to this formula. Lambda, if we calculate c by frequency, 3 speed of light divided by the shift in the frequency, if we substitute, we will get the shift in the wavelength, 1.67 into 10 to the power minus 6. So here so option C is correct here. So the next question, here we have to match the group 1 and 2 and identify the correct option. So here they have given 4 options, different spectra, that is related to electronic, nuclear and transition between vibrational states. So first option, that is electron spin resonance, ESR. Here option for electron spin resonance is given by microwave frequency, because ESR is used in gigahertz, that is for 8 to 10 hertz, 10 gigahertz. Then if it is existing in this range, ESR, electronic spin resonance, then this would relate to microwave range. Second one, nuclear magnetic resonance, NMR. Option here is radio frequency range. Option A is correct here. For ESR, option 3 is correct. Transition between vibrational states of molecule. And here NMR spectra, NMR nuclear magnetic resonance is used in the megahertz frequency range. So if it is in the megahertz, then that would relate to radio frequency. Transition between vibrational states of molecule, the range is going to be in terms of 10 to the power 12 to 10 to the power 14 hertz frequency. This would relate to option 1. Option infrared range. Option 4, it is far infrared range. Then electronic transition, that is related to the frequency range of 10 to the power 14 to 15 hertz. It is in the visible region. So option 2. So if we see these options, we can correlate the answer for this is option option D. Option D is correct. E3, Q1 and R4, S2. Next question, the separation between the first Stokes and corresponding anti-Stokes lines of the rotational Raman spectrum in terms of rotational constant B is. If we draw the Stokes and anti-Stokes lines, let us take these are the lines we are going to draw. So LHS side, these are given by Stokes lines and these are given by anti-Stokes lines. So the first line, if we take this separation, is about 6B rotational constant 6b into 6 plus 6b. This is for Stokes lines and this is for anti-Stokes lines. Then 6 plus 6, how much here? That is 12. So option D is correct here. The next one, the number of fundamental vibrational modes of CO2 molecule is. So the number of fundamental vibrational modes of CO2 molecule is 3. Out of these, 2 are infrared active and 1 is Raman active. So that means here two are infrared and 1 is Raman active. So option 3 is correct. See the number of fundamental vibrational modes of CO2, that is going to be total 3, 1, 2 infrared active and 1 Raman active. So these are the some questions related to atomic and molecular physics. I hope it is helpful for you. Thank you.